Hello everyone, welcome back to the next lecture video for Math 110 Intro to Number Theory. What we're going to talk about today is, mathematically speaking, just what are the natural numbers anyway. So just to start things off, so blackboard N is the usual symbol for the natural numbers, and it's a set starting with 0, then 1, 2, 3, and so on, adding 1 every time, forever and ever. So our convention is that we include 0, which is it's a reasonably common convention, but it just should be known that not everyone includes it. So usually when they're introduced, well, you make the comment like I just did. So other names for it to reduce confusion are the non-negative integers, which is sometimes written as z greater than or equal to 0. Or, well, there's also, for the opposite, n plus to represent the natural numbers not including 0. Anyway, so we all have an intuitive idea of what the natural numbers are, but do we really know what they are? And what really is that ... supposed to mean? So that's generally what we're going to talk about. So the plan is, let's try to see where the natural numbers come from. Then we'll try to understand the natural numbers as being the embodiment of the concept of induction. Then we'll show how to define addition and multiplication from scratch and prove basic properties about them, using only really basic properties of the natural numbers that we can all believe in. After a bit of that, then we'll look at the well-ordering principle, which is another formulation of induction, and it's a very useful thing in some coming lectures. And we'll also talk about a couple of applications. So one thing I should mention is that some of this will get technical, and it's fine if you don't follow all of it. And anyway, it's some interesting stuff to see, and just see how to get, what it's like at the bottom of things. So this is potentially one of the first times in your mathematical career that you do get to the bottom of things. Because, well, like calculus, you assumed that the real numbers existed, and really what are those? And those are a lot more complicated than the natural numbers. And, yeah, and so the natural numbers, they're this essentially foundational object that we just assume exists. And really everything that's below that is just logic, so no more math below. In other words, they're implementation details, like are we implementing mathematics inside of Zermelo-Fraenkel-Cantor set theory, ZFC? Are we implementing it in another system called type theory? Are we doing the natural numbers in piano arithmetic? We're just going to avoid these foundational questions that are at the logic level. Okay, let's start with intuitive idea number 1. And that is, and I really do mean intuition, it's this mental apparatus that we have, which allows us, just by looking at two different groups of objects, so long as there aren't that many of them, we can tell when there are a different number of them. Who knows why we have this capability? Some people think that it's because of parents wanting to be able to count their young so that they know that none of them have been misplaced. But it is something that we have. So anyway, without counting, like the second one here, has one fewer sheep in the pen. Intuitive idea number 2 is that if we have some number of members in a group, then by removing members one at a time, so in this case, sheep leaving the pen one at a time, eventually we'll be left with nothing in the group. So we started with 4 sheep, and then after 4 sheep left, we're left with none. This may seem obvious, but what if it were the case that there are just so many sheep, no matter how many you remove, there are still more sheep left over? But I guess the idea with numbers and counting is that you will run out eventually. Intuitive idea number 3 is that counting is this abstract thing that allows us to use objects of one type to represent another. So for example, as our sheep are leaving the pen, we can take a pebble and put them into the bucket. So for each sheep, we put a pebble in. So after the first sheep leaves, there's one pebble in the bucket. The next sheep leaves, now there are 2 pebbles in the bucket. And the third leaves, there are 3. The fourth leaves, there are 4. And then there are no more sheep. And these 4 pebbles in that bucket represent each of the 4 sheep that were originally there. So that is the idea of, or this intuitive idea. And then part of it is that these 4 pebbles in here are telling a story. They're telling us that there were 4 sheep that left the pen in some order. So we can also reverse this process and imagine, well, I guess at the end of the day, the sheep re-enter the pen and we start removing the pebbles again. So as that occurs and we go back in time with all these arrows reversed, eventually we'll be left with an empty bucket and all 4 sheep back in the pen. And then that represents the fact that all the sheep that left have come back. So numbers are these like fungible concepts that can stand for any number of things, and that's something that we want. So let's start looking at a more abstract thing, these abstract counts. So one thing to know is that each symbol that we have, 0, 1, 2, 3, 4, and so on, sort of by definition is 0 with 1 added to it some number of times. And it's been so long that you've learned to count that you might have forgotten this fact. But anyway, so 1, starting with nothing, you add 1, that is what 1 is. 2, start with 0, add 1 twice, that is what 2 is. And it's a little circular, but we can see that there are these 2 plus 1s right there. So anyway, each of these plus 1s is sort of this embodiment of, it's a tally mark, just a old-fashioned tally mark, just written with more symbols than you really need to record 4 things. So one consequence to intuitive idea number 2, which was that as you remove things, eventually you're left with nothing. Every element of the natural numbers ought to be written as some sort of finite expression of the form 0 plus 1 plus 1 plus 1 plus so on. Because given your number, you can start removing them, like subtracting 1 repeatedly until you're left with 0, and we just keep recording the plus 1s that we needed along the way. With this intuitive idea in mind, and also to avoid some circularity in some future discussion, let's avoid plus. So instead of plus 1, let's have this simpler operation that ends up being sufficient for everything, and that is S of n, which is the successor to n. Using addition, S of n is just n plus 1, but we're going to be forgetting addition for a while and just work with successors. So 1, it can be defined to be the successor to 0. 2 is the successor to the successor of 0. 3 is the successor of the successor of the successor of 0, and so on. So also, I guess as a mnemonic, S is like inserting an additional stone into a bucket. So given the empty bucket, which is 0, then the successor to the empty bucket is a bucket with 1 stone. A successor to that bucket is a bucket with 2 stones, and so on. So one consequence to intuitive idea number 2, just like before, is that every element of n is the iterated successor of 0. So the successor, the successor, the successor of so on of the successor of 0. For some finite sequence of successor. So a takeaway so far, just to summarize, is that elements of n may as well just be expressions involving s and 0. So there is nothing more fundamental than the symbolic expression that of s's and zeros. So for example, 5, we just say it is s of s of s of s of s of 0. There's no more than that. There's no independent meaning, and one reason that this should make some amount of sense is that the symbol itself is the embodiment of the number. There are 5 s's there, so it is 5. And so that is a reasonable way to go. I found this to be somewhat of a mind-bending idea at the beginning, but it's also sort of elegant in itself. So we've looked at the first 2 intuitive ideas. which led us to the idea that every natural number ought to be representable as some finite sequence of successors of 0. So what is the role of intuitive idea number 3? Like, what does it actually mean to count? So one possible answer to this is induction. And there are a number of formulations of induction, and I'm going to give you a very general one, which is suitable for something called inductive definitions, which you might not have seen before, because usually you just learn about proving things through the principle of induction. But this is a way to create new things from the natural numbers. Okay, so the way that this works is that given 3 things, then there are 2 conclusions you can obtain from that. So the 3 things are, 1, for every natural number, we associate to it some set of some kind. So there's A0, A1, A2, and so on, all of these sets. The second thing is that we're assuming that we're given some element A0 of the 0th set. So something to start us off. And when you're proving things, this is known as the base case. And then for each natural number, we want to have some function that takes elements of the AN set to the next set up. So in some ways, this is like the successor function. It's the thing that, given something in level n, or like the nth set, will give us something in the successor set. And maybe to make this more in line with what I said before, let's write that as S of n. So this is known as the inductive step in a proof. Okay, so then what are the conclusions? Well, 1, for each n, we can get some element an of the set an, where a0 is the thing that we started with in the base case. And also, for each n, we have the property that the a for the successor of a number is the result of applying f of n to a of n. So to annotate this a little bit better so you can see what's going on, we have a0, a1, a2, a3, and so on. And each of these is contained in a particular set. So a0, a1, a2, a3, and so on. So these are all elements. And then the relationship between all of them is that the next one comes from applying the previous function. And so on. So this inductive definition, it's sort of like an axiom. It's just something we assume. There's no underlying proof to it. It's just what we want the natural numbers to satisfy. And one reason that we believe that this sort of thing ought to hold is that we can imagine how we'd actually compute it, just as a procedure. Like to get A3, we take A0 and apply F0, and then we apply F1, and then we apply F2. And then that gives us A3. And so we imagine that for any number, no matter how large, given enough time, we'd be able to compute what that number is supposed, or what that an is supposed to be. So this is the principle of inductive definitions, and we're going to make use of this. So given that principle of inductive definition, let's look at how we can define addition, which remember we sort of threw away because we wanted to reduce everything to very simple objects and concepts, which was the successor. So how might we conceptualize addition? So 3 plus 4, for example. We could start with a bucket of 3 objects, and then imagine that we then take each of the stones that are in the second bucket and put them into the first bucket, one at a time. So symbolically, 3, remember, is the successor of the successor of the successor of 0, and 4 is similar. And to have the idea of taking all the stones in the bucket for 4, we can take 0 and kind of poke a hole in the expression, and then take the bucket for 3 and plug it right in. which is represented over here, where we have the 4 stones that were inserted from the second number onto the bucket from the first number. And so this is the number 7, of course, because there are 7 successors here. So in other words, if the S's are like tally marks, we just simply append the tally marks across and we forget about the 0 in the second one. So that's all well and good, but we somehow need to eventually use inductive definitions because this is really not a definition on its own. I've just shown you how to add 3 and 4, but we need to know this works in general. So here's an almost definition. I wrote it as a definition, but we're going to patch it up in the next slide. And so let's define addition to be the binary operation for n. So it takes 2 natural numbers and produces a natural number, subject to 2 rules. Rule A is that a plus 0 is just defined to be a, and rule 2, or B, is that a plus the successor of b is just defined to be the successor of a plus b. This may seem like a couple of odd rules to use. At least the first one makes sense as a rule, but it's not super clear where the second comes from. But it does come from this example, and I'll show you how, by way of showing you how adding 3 would work. So let's say we have a number a, and we're adding 3 to it. So by rule B, the successor on the outside of the second number is pulled out to the whole outside. And then by rule B again, the successor of the second number, 2, that's in here, gets pulled out. And then there's another successor, and we pull that out. And then we have the plus 0, so we apply rule A. And what we have is a plus 3 is the successor of the successor of the successor of A. So it's kind of following the scheme from the example. But is it okay actually defining addition in terms of itself? Because addition is showing up on both sides of this equation. And that is what inductive definitions are for. So let's see how that can work. Here are our rules from before that we claimed would work. And so let's formally write this out as an inductive definition. And so in this box here, I have what it means to do an inductive definition so that we can refer to it. Okay, so the first thing is we need to choose some sets for every natural number, and that's easy here. We're just going to choose n. It's not going to change, or I mean the natural numbers. It's not going to change in any way. It's not going to vary on n. The second thing is we need to choose an element of the 0th set. So let's just set the 0th set, or the 0th element to be just a itself, which of course is an element of n. So it's an element of a0. 3, we need for every natural number a function that carries something from an to an plus 1. And that's a lot of freedom there, but here we're just going to take the successor function itself for every single n. So f0, f1, f2, they're all just s. Okay, so given these 3 things, which we've now supplied, then we get 2 conclusions from the principle of inductive definitions. The first is that for each n, we have some number an that's in each of these sets, with where additionally a0 is chosen to be just a itself. Okay, that was 1. And then the 2 is that for each n, we have the property that a sub the successor of n is equal to f of n of a of n, but f of n was just chosen to be the successor function. So the rule is a sub sn is s of an. Okay, so given that, we define a plus b to be a sub b. So the bth number that the inductive definition principle gives us. So I'm not expecting it to be immediately clear that this is exactly what we want. And it took some thought to come up with this application of this principle in this way to get addition. But it does work, and we can see this, the following. So let's check that this actually does match the rules. So rule A was that A plus 0 is A. So let's check. So A plus 0, we set to be A sub 0, and A sub 0 we set to be A. So A plus 0 is actually A. So that's good. And for B, which is that A plus the successor of B is the successor of A plus B. So A plus SB is, as we defined to be, A sub the successor of B. And according to 2 in the conclusion of the induction principle, A sub S of B is S of AB. And so S of AB, as we have defined, is S of A plus B. So property B also holds. So this was actually enough to define an operation. And so that's one of the powers of induction, what the natural numbers let us do. One thing I'm not mentioning is that there's precisely one operation that satisfies these 2 rules, but let's just sweep that under the rug for now. Okay, so now that we've defined addition from scratch, let's prove that it has a bunch of properties that we come to expect, like commutativity and associativity. So the sibling to inductive definitions that we need for this is induction, which you already know. So inductive definitions are element-based versus induction, which are property-based. And like they're really kind of the same thing, but I'm going to restate it for convenience. So induction is that given 3 things, then there's a conclusion. The first thing is that for each n, there's some statement P of n that depends on n. Property 2 that we need to have satisfied is that P of 0 is true. And the third given is that for each n, P of n implies P of the successor of n. So 2 and 3 are also commonly known as the base case and the inductive step. And the conclusion is, with these 3 givens, that for each n, P of n is true. So it's just universally true for all P. I kind of like to think about these as dominoes sometimes. I know you don't need this because you know induction, but so if we have domino 0, 1, 2, 3, and 4, 2 is that, if P of n is that the nth domino will be knocked down, and P of 0 is true because I knocked the first domino down, and 3 is that for each domino that falls down, it will knock down the next domino. Then the conclusion is that for each n, that domino will be knocked down. So in particular, every domino will eventually fall. Right. So just like inductive definitions, this is just an axiom that we take on faith. We know what it's like to count things in the world, and we have no reason to believe that counting doesn't work this way. Though strictly speaking, this principle of induction can be proved from the principle of inductive definitions. So, the natural numbers, what are they? Well, we can say that 1, they're successor and 0 expressions, and they're expressions that satisfy these induction principles. Like, that's it, full stop. No more about natural numbers than this, as far as math is concerned. So that's kind of cool. So let's see if this actually holds any water by proving some basic properties, seeing that actually works. So that's what we'll do over the next few slides. So up in the left corner, we're going to keep track of everything that we know so far about addition. So first we have the 2 things that we have by definition, things that are basically just assumed through the induction principle. So then we'll augment it with theorems. So the first theorem, for every natural number, 0 plus that natural number is the natural number. So surprisingly, this does need proof. It's not just true by definition. Okay, so we're going to apply induction, so we need to know what our property is going to be, or what our statement is going to be. So P of n is the statement 0 plus n equals n. And that's what we want to prove is true for every n, because that is exactly what we're trying to prove for the theorem. So the base case, that is when n is 0, and p of 0, substituting 0 in for n, is 0 plus 0 equals 0. So if we look up at definition a plus 0 equals a for every a. So if we substitute in 0, that's definitely true, so the base case holds. Now to the inductive step, which is that for all n in the natural numbers, then whenever p of n is true, then p of the successor of n is true. What we're trying to show is that 0 plus Sn equals Sn, just substituting in Sn for n. Okay, so suppose now that n is some arbitrary natural number and that p of n is true, because we're trying to show that for all n, p of n implies p of Sn. So, so we start with the left-hand side of p of Sn, and that is 0 plus Sn. And then by definition b, we can pull the successor from the second argument to the outside. So that then becomes the successor of 0 plus n. And then 0 plus n is in there, and we are assuming p of n, and Pn is that 0 plus n equals n. So we can replace that 0 plus n with n on the inside, and that leaves us with Sn, which is exactly what we wanted. So p of Sn is true. So given these three things that we just showed, we can then apply the induction principle and conclude that for all n, p of n is true. And this is exactly what we wanted to show. So we now know that we can add 0 on the left side in addition to the right side to get the number that we started with. Okay, so that's now been added to the list. What's our next theorem? And this one is that for every pair of natural numbers, a and b, that if you take the successor of a number and add the second number, then that's the same as adding the successor of the second number. Okay, so again, this is going to be an induction proof. So let's suppose that a is some arbitrary natural number, and so it suffices to show that for all b, s of a plus b is a plus s of b. I'm just taking the first for all from this and leaving the rest. That's our statement. So what we are going to do is have p of n be the statement the successor of a plus n is a plus the successor of n. So it's this internal part of this for all statement, but with n in place of b. So now we have what our p is. Now let's look at the base case. That is p of 0. And so substituting 0 in for n, we have, well, s of a plus, what we want to show is that s of a plus 0 is a plus s of 0. Okay, so let's go through equationally and prove this. So we start with s of a plus 0, and then by applying definition a, we can remove the 0. Then applying definition a again, but in reverse, we can add a 0 inside. And then applying b, we can, in reverse, we can take that successor and then rewrite it with the successor on the second number. And so that's exactly p of 0. So we have proved the base case. Now the inductive step. So what we want to show is that for all natural numbers, p of n implies p of Sn, like usual. So let's assume that n is an arbitrary natural number and that p of n is true for it. So what we are wanting to show, and I'm just taking p of Sn here and expanding it, is that the successor of a plus the successor of n is a plus the successor of n. So that is what we want to show. And again, we can do this equationally. So we start with the left-hand side of what we want to show, and then we take definition b and take that successor on the second argument and pull it out. And then we apply the induction hypothesis, Pn, which we remember is, well, Pn right up here is S of A plus N is A plus S of N. So we see that right there, and we replace it. And then lastly, we take the definition again, and we take the S that's on the outside and pull it in. And we get the right-hand side of what we wanted to show. So the induction step is valid. Okay, so then, given the three things, we apply induction, and we can see then that, well, for all n, P of n is true. And that is a restatement of what we wanted to show, and this suffices to show right here. So I hope you're seeing this sort of structured way I'm writing proofs. I find it's useful to be as careful as possible and to try to organize things in this indented way, to know what you're assuming and what you're trying to show and so on. Okay, so now for theorem 3, what we're going to show is the famous property of commutativity, which makes some intuitive sense because, well, it doesn't matter in which order you put stones into a bucket, you'll have the same number of stones in the end. So for this, let's suppose A in the natural numbers is arbitrary, and it suffices to show that for all B in the natural numbers, that commutativity holds. So we set our statement, which is that P of n is A plus n is n plus A. So let's check the base case. That is A plus 0 equals 0 plus A. And this is some applications of definitions and theorems. So equationally, we have A plus 0 through definition A is A. And then through theorem 1 in reverse, that's 0 plus A. So that is done. Now the inductive step, which is, as always, for all n, P of n implies P of the successor of n. And so writing this out, that's for all natural numbers, n, whenever A plus n equals n plus A, then A plus the successor of n is the successor of n plus A. So, since this is supposed to be a for all, let's have n be some arbitrary natural number, and let's suppose the hypothesis that it commutes with A through addition. So we can do this equationally again. So we start with the left-hand side, and we apply B to pull the S out, and then we apply our hypothesis to commute the addition on the inside of that S. And then we apply definition B to push the S to the end of the expression. And then we apply theorem 2 in reverse to bring the S on the A to the S on the N. And that is exactly the statement we wanted to show. So I should just tell you that the way I found this was I knew what I needed, and then I kind of searched through everything that seemed reasonable until I made this connection from beginning to end. It's except for having a little bit of intuition from being in this business for a long time, it just takes some work to figure out how to get from here to there. Okay, so now that we've had those three things, by induction then, we know that P of n is true for every n. And that is exactly what we wanted to show. So that is commutativity of addition. So there's just one more theorem I'm going to show you in this elaborate way, and that is associativity of addition, just to round out all the main properties. Okay, so it's actually, it's straightforward. If you've been following along so far, you probably could do it yourself, and maybe you should give it a, pause the video and try your hand at it, and maybe cover your screen or rewind a bit so you're not looking at the solution. Okay, there are three universal quantifiers here, for all A, for all B, and for all C. So let's suppose A is some natural number, arbitrary. So then P of n will be the statement, which is, and n will stand for C, which might be a little confusing. For all b in the natural numbers, a plus b plus n equals a plus b plus n. So we're going to induct on the third thing that shows up in the expressions. So the base case, p of 0, is a plus b plus 0 is a plus b plus 0. And this is a simple matter of applying definition A. And I don't need to run through it. You can pause and read it. So then the inductive step is, like always, for all n and n, if p of n, which is written above, then p of the successor of n, which I've written out right here, is a plus b plus the successor of n is a plus b plus the successor of n. So we can equationally reason. So starting with the left-hand side of what we want to show, we can apply definition b in the forward direction to pull the s to the outside, then apply the induction hypothesis p of n to the interior of s, which reassociates the parentheses. Then we can apply b in the reverse direction to push s back onto the inside. And then we can apply a b once more to push s all the way to the last argument. And that gives us p of s of n. Hence, by induction, we now know that for all n and for all b, that a plus b plus n equals a plus b plus n. Since it doesn't really matter what the variable names are, and also when you have for alls in sequence, you can rearrange the variables and it's logically equivalent, then this is what we wanted to show. Okay, so let's recapitulate. From fundamental principles, what we have are 2 definitions and 4 theorems, where definition A and theorem 1 are saying that 0 is an additive identity on both sides. That's a very important fact about the relationship between 0 and addition. And then the last 2 theorems we showed are that addition is commutative and also addition is associative. So these are the basic algebraic properties of addition for natural numbers. And we did that all through careful formal reasoning, and we only assumed that n, like, sort of literally is expressions involving only s and 0 that satisfy certain induction principles. Of course, there's some stuff that's being unsaid, which is what exactly are the foundations of math that we're basing everything on. But at least in principle, everything we did carries over from one foundational system to another. Okay, so now that we've seen all this stuff about addition, I'll just give you a cursory overview of what multiplication would be. So first of all, multiplication for n, which I'll write using the standard juxtaposition of symbols, for or a dot, I guess I could do sometimes if I want. So it's the binary operation subject to 2 rules. Rule 1 is that if you multiply a number by 0, you get 0. And rule 2 is that if you multiply a number by the successor of a number, then we could multiply those numbers and then add the first number. I find this is a lot easier to understand geometrically. So if we have a rectangle, which is b plus 1 on one side and a on the other, so successor of b on one side and length a on the other, then we can break this rectangle up into an a by b rectangle and an a by 1 rectangle. And a by 1, of course, has area 1. So that is this formula on the right side over here. So like before, we can turn this into a completely valid inductive definition. I'll skip those details here. And so, yeah, so it's this well-defined thing. And so we could go on and prove a whole host of other properties, like multiplying by 0 on the other side of a is 0. Multiplying a by 1 on either side is the original number. So 1 is an additive identity, or I mean a multiplicative identity. We can show that multiplication is commutative, that's associative, and that it distributes over addition. And so on and so forth. So rather than doing this in lecture, one thing I think would be a good experience, at least I enjoyed it, is proving these things on a computer using a language called Lean. And so the natural number game is an online version of Lean that has been simplified, and it's all about proving all of these basic properties of the natural numbers. And in fact, I basically had you we ran through together a bunch of your first proofs that you do in that game, but you do it in this other language, Lean. And I should mention that if you do this, then and you let me know how many worlds you complete, that will count as a little participation bonus points. Now that we've gone through basic definitions and shown how we can create them, and hopefully that gives you a sense of what the natural numbers truly are, let's go through a couple of other properties. And they're just induction again, but it's nice to have them in some other formulations because it can be useful in certain applications. So, an inductive set. A subset of the natural numbers is called inductive if two things hold. One, that it contains 0, and 2, whenever it contains a number, then it also contains that number plus 1. From now on, I'm going to write n plus 1 for the successor, because now we know addition works and it's fine, so there's no reason to have this additional operation. Okay, so the thing is, like, inductive sets are a little boring because they're all just n. But that's a nice property because if you have some set and you can prove these facts, then you know it's n. Okay, so let's prove that this is the case, and it's just a simple matter of induction. So one thing to know is that this conclusion that we want to prove, that S equals n, by the principle of extensionality, it's actually an axiom from set theory. To prove that two sets are equal, the definition of that is that for everything, that thing is in the first set if and only if it's in the second set. So being an element of one thing is equivalent to being an element of the other. Extensionality comes from this philosophical idea of things being just like a thing is how it interacts with the world. And the only way in which a set interacts with the world is what elements does it have. So you ask it, do you contain 5? And the answer is yes or no. That's all there is to it. So if they behave in the same way, they are the same. That's set theory. So let's simplify this logically. Every n is an element of the natural numbers. And also, well, we know that S is a subset of n. So we can simplify this to just checking that for all n in the natural numbers, then n is an element of S, because the opposite direction is already satisfied. So to do this, let's induct on n. So the base case is that 0 is an S, and that certainly holds because that's an assumption of it being an inductive set. And then the inductive step is that suppose that n is in S, we need to show that n plus 1 is in S, because that's the successor of n, of course. And that holds by 2 because that's just exactly what it is. And then that completes the proof because we completed the induction. Okay, so those were inductive sets. And another useful sort of inductive principle is the well-ordering principle, which intuitively is very straightforward. It's that whenever you have a non-empty set of natural numbers, then there's a minimal element or a least element. And we can just sort of imagine why we would think this is true. And that's if we imagine all the numbers lying in a number line, and we imagine each of the elements of S are marked, then we can just walk along the number line until we hit the first thing that is an element of S, and then that's the least element because there's nothing before that. And we know that we will run into something because the set is assumed to be non-empty. So now the trick is we'll understand what all these words mean in a technical way, and then actually prove it. And that's what I want to do. So one thing is, what does least mean? So least is that, so an element is a least element of a set if for every other element of the set, it could be the same element, but for every element of the set, then that least element is less than or equal to it. So just for sake of exhaustiveness of definitions, what does it actually mean for n to be less than or equal to m? And it has a straightforward definition, which is nice. So we say that n is less than or equal to m if there's some k such that when you add k to n, you get m. Because this represents the fact that in some way m is to the right of that number on the number line. So, so n plus k is m, and that means m is bigger, at least as large, because k could be 0. Okay, so before getting into a proof, one thing I want to mention is an alternative formulation of this well-ordering principle that might not be obvious if you haven't seen these things before. So underlying this is this thing called the axiom of restricted comprehension. You don't need to know that name. And that is that there's this correspondence between statements that are indexed by natural numbers and subsets of natural numbers. And the way this correspondence works is, well, on one hand, if you have a bunch of statements for every natural number, you can form a set of all those natural numbers for which the statement is true. But also, given such a set, you can get a bunch of statements by having the nth statement just be the question, is n an element of the set? Okay, so P, I guess, is like the sort of indicator of whether or not an element is in the set. Okay, so given that for all n we have these statements, and also that there exists some m such that P of m is true, so at least one of the statements is true, then there exists some m prime such that two things hold. One, it satisfies its statement, and also for every other number that satisfies a statement, then it's at least as large as m prime. So in other words, there is a least natural number that satisfies this family of statements. So that's an alternative formulation. I thought I'd mention it. Okay, so to prove this, it's useful to have a lemma. And this lemma is a much more restrictive version. So S could be infinite for all we know. So instead, we're going to consider finite sets. So the lemma is for every n, if S is some subset of the first n plus 1 natural numbers, so the set of all k where k is less than or equal to n, and if that set is non-empty, then S has a least element. Okay, so intuitively speaking, the idea again is the way we get that least element is we walk along in increasing order of natural numbers, and we know that we can stop at the nth one because there are no more numbers beyond that. And also it's non-empty, so we will run into one. So anyway, we need to formalize this to get a proof. So what we will do is use the inductive set point of view for induction, just to give it a whirl. So I found this to be a surprising definition when I first saw this. So let's let A be the set of all n where the lemma is true. Okay, because we want to show it's true for all n, so we define the set of natural numbers of the things where it is true. We'll show it's an inductive set. Because inductive sets are equal to the natural numbers, then that shows that it's true for every n. Okay, so I've written the statement of the lemma inside this set builder notation. Okay, so we're going to show it's an inductive set. So the base case is that we want to show 0 as an element. So so looking at 0, that's the statement for all non-empty S in just the set containing only 0, then S has a least element. So we're assuming that S is a subset of the set consisting only of 0. and we're assuming it's non-empty. And skipping being ultra formal, if you have a non-empty subset of a one-element set, then it just is that thing because they have the same number of elements. So 0 is its least element because it has nothing else. So that's the base case. For the inductive step, what we can do is, we're supposing n is an element of A, and we want to show that n plus 1 is an element of A. So let's write out what it means for n to be an element of A. That was that for all non-empty S then, and so on and so forth. So let's say that S is an arbitrary one of these subsets. And we're assuming that it's non-empty. So what we want to do is now show that S has a least element. So the way we do this is we consider two cases. So case 1 is whether S is simply the one element set consisting of n plus 1. The reason why we're considering this case will be clear when we look in the second case. So if it is just n plus 1, then, n plus 1 is its least element, because that's just like in the base case, that's all it has. For case 2, so S is not n plus 1. What that means is it must have some other element in it. So we can reason that if we intersect S with the elements 0 through n, then there is some other element in there, right? So that is a non-empty set, this S prime that I've defined as this intersection. And also because it's an intersection, we know that S prime is a subset of both of the things that are being intersected, and in particular the second one, the set of 0 through n. So, since we assumed that n is an element of A by this induction hypothesis, then S prime has a least element. Let's call that M. So now let's reason with some inequalities. So we know that M is less than or equal to n because S prime only has things from 0 through n. Secondly, we know that n is less than n plus 1. That's because it's the successor, and that is how that goes by definition. Like if you look back to the definition of less than or equal to, that's when k is 1. So since this is true, then that means that M is the least element in S, because it can't be n plus 1 because n plus 1 is bigger than it. Okay, so that completes showing that M is actually the least for S. That completes case 2. Both cases are handled, so the inductive step is completed. And so, since we've shown the two properties of it being an inductive set, we can conclude by that theorem that A is n, and that suffices for this lemma. Okay, so now that we've proved this lemma, the Welder ordering principle itself is fairly straightforward to prove. Okay, so suppose S is a subset that's non-empty that is arbitrary, because we're trying to show for every S that's non-empty, then there's a least element of it. Okay, so because it's non-empty, that means that there is some arbitrary element of S that we can just have on hand. So let n be one of those elements in S. Okay, so then let's let S prime, like in the lemma, be S intersected with the first n plus 1 natural numbers. So because n is in S and n is also in the second set, then we know that n is in S prime, so that's why it's non-empty. And also we know that S prime is a subset of the second thing that we intersected with. Okay, so by this lemma then, we can immediately apply it and conclude that there's a least element M for S prime. It might not be a least element for S itself, and that's what we need to show next. But I should just mention that S prime of course, is a subset of S also because it's the first thing being intersected with. So M is an element of S. So the claim is that M in S is least. Okay, so the definition of least, remember, is that whenever you have an element K in the set, then that element is at least as large as the supposed least element. So if we show that that is true, then we are good. Okay, so I'm going to break this into two cases. The cases are whether or not K is less than or equal to N. The second case is just the negation of the first. Okay, so if K is less than or equal to N, then because it is in the second set in the intersection, that means it's in S prime. Okay, and since M was least for S prime, we can conclude by the definition of least that M is less than or equal to K. Okay, so that was what we wanted to show, so that case is handled. So now case 2, N is less than K. So for this, since M is less than or equal to N, because M is an element of S prime and we intersected with this set from 0 to N, and since we assume N is less than K, then we can just compose those two inequalities together and get that M is less than K, which is, or less strongly, that implies that M is less than or equal to K, which was what we precisely wanted to show. So that's that. So both cases were handled, so M is in fact least for the set S, and so S has a least element, this M that we found. And that's well ordering. So well ordering, it's a very useful property, and it can be used for doing things like showing that division is something that we can define, which is a bit more awkward to show directly through induction. So that's why we have it. Okay, so I want to show you some examples of some of these principles. So the first one is that every number, okay, so for all n in the natural numbers, there's some k such that n equals 2k or n equals 2k plus 1. Or in other words, n is even or odd. So that would be a nice thing to know, right? Okay, so the way that we're going to prove this is through well ordering. And we're going to basically suppose that it was false, which means that there is some number that's neither even nor odd. Then we can take the set of all numbers that are neither even nor odd and take the least one, and then show that we can, because it's the least one, and everything below it is even or odd, we can then show it was actually even or odd too, and then contradicting the whole thing. It's a lot of writing, but it's more straightforward conceptually than it ends up being in practice somehow. Okay, so by contradiction, we'll assume the opposite, which I've written out as there exists an n such that for all k, then both n is not 2k and n is not 2k plus 1. So it's neither even nor odd. Okay, so given this assumption, then if we take the set of all n for which this is, for which the conclusion of that hypothesis is true, then that's a non-empty set. Okay, so then we apply the well ordering principle, and so then there's a least element in that set. So let M be that least element. So then we consider two different cases, and one of the cases is two subcases. So case 1 is that this least element is 0. Well, that can't be because it's clearly even. It's just 2 times 0. So it contradicts the fact of M being an S, because if we plug 0 in for k, then the first thing is false. So for case 2, that's M being the successor of some number. So yeah, the cases are 0 or successor. So if it's the successor of some number M prime, then since M prime is less than M and M was least, that means that M prime is not an element of S. So let's consider two cases. The two cases are from M not being an S, which are it's the or right here that we're going to split on. So case 1 is that there's some number L that I'm writing for K to reduce some confusion with multiple letters. So there's some L such that M prime is 2L. So case A is that M is even, or M prime is even. So we can calculate then that M, which is M prime plus 1 by assumption, is then 2L, substituting in that for M prime, plus 1. But that contradicts M being an S, because we can set K to be L, and this one is contradicted. Okay, so that can't happen. So case B is when M prime is odd. So there's some L in N such that M prime is 2L plus 1. And so we can then calculate that M is M prime plus 1, which is then substituting in for M prime, 2L plus 1 plus 1, and then through a little bit of algebra, we see that's 2 times L plus 1. So that contradicts, again, M being an S, this time with K being L plus 1. Okay, so both of these cases were contradictions. So case 2 results in contradiction, and also we saw case 1 results in contradiction. So everything that we even considered resulted in a contradiction. So therefore, we couldn't assume what we assumed by contradiction. And in fact, it's true that every number is even or odd. What a surprise, right? Okay, so that is an example of well ordering and how you might use it. And basically, I was sneaking in the fact that we can divide by 2 and either have remainders 0 or 1. It's a little preview to the more general thing in a future lecture. Okay, and just for sake of having an example of induction to finish things off, and this is the last thing, I'm going to go through a very standard induction proof, which is something that Gauss figured out. Well, he figured out the formula when he was a school child. The story is amusing. The school teacher assigned everyone to sum like the numbers 1 through 100 longhand, and then Gauss just kind of sat back, stared into space, and realized that he could add the first number to the last number and the second number to the second to the last, and so on. And they all gave you the same thing. And then there were n over 2 copies of that, so you could just multiply that all together and then get what the sum would be. And he did it in a couple of minutes. And the school teacher was angry that then Gauss had nothing to do. And I should also mention, okay, so that is, the insight of Gauss, one of the greatest mathematicians ever. Induction cannot help us find a formula like that. All it can do is help us prove it. I mean, you need some sort of insight or something called abductive reasoning, where through a pattern you figure out some sort of theory for what explains it. So let's just prove it now that we have some possibility for the formula. And if this formula is right, then, we'll prove, well, if the formula is not right, then we can't prove it. Also, what does dividing by 2 mean here? We're just going to assume that we know what that means at this point, even though we've not defined it. We've been to elementary school. Okay, so let's do this by induction on n, and we'll just do this as plain old induction. So the base case, which is when n is 0, is it's on the left-hand side, it's the sum of no numbers, so that's 0. And on the right side, we substitute 0 in, and we get 0 times 0 plus 1 over 2, and both sides are 0. That's done. For the inductive step, so now we assume that the formula is true for some random n, and we want to show that it's true for n plus 1. So that's our assumption, and now we do this equationally. So we start with the left-hand side of the equation we want to show, reparenthesize it so that we can see that 1 through n is in there, the sum of them. We substitute in what we're assuming, do a little bit of algebra to bring it all together, and then commute the top two and parenthesize things even more. And then we see that the successor of n times the successor of n plus 1 over 2 on the right side, which is substituting s of n for n. Right, so then that proves the induction step. And so by induction, for all n, the formula holds. And so that's that. Okay, so this is more what Appendix A in the textbook is about. But I showed you the other stuff because, you know, this is a good time to finally see what the natural numbers are. And also you've seen induction before, and so this is the next step, so to speak. Okay, so let's summarize. One thing that we talked about is the natural numbers is the sort of fundamental notion that are sort of trying to capture some intuition we have about counting and the fungibility of the abstract notion of number. And so they just are what we want them to be, and they're introduced axiomatically. And now you've seen sort of some of the bare bedrock of mathematics. Then we also saw the induction principles and defining things by induction, which you've probably not experienced before. And inductive definitions are very useful in a lot of mathematics. And using that, we just from scratch defined addition and multiplication, and we proved some properties to show that it can be done. And also to give you some examples of what like a structured mathematical proof could look like. And we did all that just by assuming that we had 0, and we had this abstract idea of taking successors, and we applied the axiomatic inductive properties. And then lastly, we talked about well-ordering of the natural numbers, that non-empty subsets have least elements, and we gave some examples of that. So anyway, thanks for coming by, and I'll see you next time.